Now I start my oral presentation. Good afternoon, experts and teachers. I am Kening Yan, a doctoral student from University of Science and Technology Beijing. The topic of this presentation of expanded graphite, erythritol from stable composite phase-changing materials with high thermal response speed and high latent heat for photothermal conversion. Today, I will introduce the following two parts, including the research background and the research results. The first part is research background. In recent years, due to the over-exploitation of ecosystems and the overconsumption of fossil energy, the problems of environmental pollution and climate change have brought a greater impact on people's daily life. Therefore, the focus of energy research has gradually shifted from fossil energy to renewable energy. Among them, the advantages of solar energy, such as universality, cleanliness, huge energy and long-term use, have been widely valued by people, but the discontinuity of solar energy restricts its further development. The use of phase-changing materials for energy storage can will solve the problem of discontinuous of solar energy. Phase-changing materials are divided into organic, inorganic, and eutectic phase-changing materials. Among them, organic phase-changing materials have been widely used in the field of medium and low temperature due to their advantages such as low self-cooling, high energy storage density, low corrosion, and high chemical thermal stability. However, the problem of its low thermal conductivity and easy leakage needs to be further solved. For energy storage systems, improving the thermal conductivity of phase-changing materials is the key to enhancing the thermal response characteristics. There are three methods for enhancing the heat exchange of phase-changing materials: encapsulation with a high thermal conductivity power skeleton, adding high thermal conductivity enhancements, and using microcapsules with high thermal conductivity material as shell material. The use of porous material encapsulation has the advantages of simple preparation process, low cost, good compatibility, and good cycle stability. The porous skeleton uses capillary force to encapsulate the phase-changing material, which has a three-dimensional interconnected thermal conduction path, which can improve the thermal conductivity of the phase-changing materials. The measurement principle of the third harmonic method is to input a periodic alternating current with an angular frequency of 1 omega to the sensor. Due to the Joule effect, a heat flow with an angular frequency of 2 omega is generated, heating the sensor and sample, resulting in a temperature wave with an angular frequency of 2 omega. A current with angular frequency of 1 omega and a resistor with an angular frequency of 2 omega work together to produce a harmonic voltage with an angular frequency of 3 omega. The third harmonic voltage contains the property information of a sample to be measured, and the thermal conductivity of the sample to be measured is obtained according to the relationship between the harmonic voltage and the frequency. Next, some experimental results are presented. The research results firstly introduce the preparation of energy storage materials. The phase-changing material is erythritol, which has the advantages of high latent heat of phase change, good cycle stability, no toxicity. Expanded graphite is selected as the porous encapsulation material, which has the advantages of high thermal conductivity, lower loading capacity of phase-changing materials, and reduce the subcooling of phase-changing materials. The preparation process is as follows. Firstly, the erythritol was heated at 116 degrees for 10 minutes to melt the phase-changing material. The expanded graphite was then heated at 100 degrees for 30 minutes to remove moisture. Then the two were mixed, heated, and adsorbed at 116 degrees for 24 hours, with stirring every 8 hours. Finally, press the tablet with a diameter of 13 mm and a thickness of 4 mm, using the capillary force of expanded graphite. The loading of erythritol is from 19.4 to 19.5%. Through leakage experiments to determine the maximum loading of phase-changing materials, 6 samples with different phase-changing materials loadings were heated at 200 degrees for 2 hours. The maximum loading of erythritol was determined to be 95%, and the addition of expanded graphite was 5%. By SEM, the microscopic morphology of expanded graphite raw material and 5% expanded graphite erythritol composite phase-changing material was characterized. From figure A and B, it can be observed that the expanded graphite exhibits a worm-like structure, which is connected by a large number of disordered graphite neocytars through van der Waals forces. After the expanded graphite is compounded with erythritol, its surface and internal pores are filled with the phase-changing material due to the capillary force, and the phase-changing material is successfully loaded. Then the structure of composite material was characterized, and the most probable diameter of the expanded graphite was 2.6 nanometer through nitrogen adsorption and desorption experiments, which belonged to the range of micropores. From the XRD results, characteristic peaks of erythritol and expanded graphite can be seen, and no new characteristic peaks appear, indicating only physical bonding. The FTI results shows that the chemical structure of erythritol didn't change after the addition of expanded graphite, further proving that there was no chemical reaction between the materials. For phase-changing materials, its phase-change characteristics are worth studying. It can be seen that with the addition of different mass fractions of expanded graphite, the latent heat of phase transition of erythritol doesn't change much. The range of latent heat of melting is 264.6 to 219.52, and the range of latent of freezing is 207.17 to 238.52. It shows that the as prepared composite phase changing material exhibits excellent phase change properties. Phase changing materials have the problem of low thermal conductivity. It is of greater significance to study the effect of different mass fractions on the thermal conductivity of erythritol in practical applications. The effect of increasing the thermal conductivity of erythritol with the mass fractions of expanded graphite was measured by the third harmonic method. The mass fraction of expanded graphite is 0, which represents pure erythritol. The thermal conductivity increased from 0.6 to 5.97, which was 8.95 times higher than that of pure erythritol. Next, the mechanical stress of the composite phase-changing material was measured using a universal testing machine. Among them, it can be seen that 5% expanded graphite erythritol has the highest compressive stress, which is 14.41, following excellent mechanical stress. The heat storage and release rates of phase-changing materials directly reflect thermal energy utilization in practical thermal energy storage applications. Therefore, constant temperature heating cooling was used to reflect the addition effect of expanded graphite. Considering that 5% expanded graphite erythritol has the best phase change properties, mechanical properties, and the thermal conductive properties. This material was compared with erythritol, and an infrared camera was used to observe the thermal response properties. Through experiments, it can be clearly observed that the composite material has a great heat storage and release rate because the thermal conductivity of the composite material has been greatly improved compared with pure erythritol. In order to more intuitively digitize the thermal response speed of the composite material, the relationship between the surface temperature on the sample and time was plotted. It can be seen that the composite material has a greater thermal response speed. In the thermal energy storage stage, erythritol increased from 28.11 to 66.7 degree, and the composite material increased from 27.57 degree to 87.18 degree. In the thermal energy release stage, erythritol decreased from 25.25 degree, and the composite material decreased from 83.86 to 23.94. Thanks to all experts for your attention. Criticism and corrections are welcome.